nearly 20 years of experience, his research spans machine learning, computer vision, VLSI CAD, cyber physical systems, and quantum computing. He has published more than 200 papers, filed 6 patents, and supervised 24 PhD scholars. His work is supported by agencies like DST, DRDO, MEIT, and companies like Intel, TCS, and AWS. Dr. Chakraborty is a recipient of several prestigious awards, including the DST Boy Scout Fellowship, INSA Visiting Faculty Fellowship, JSPS Award, and Shiksha Ratna Award. He is a fellow of WBS&T, COMSIS, and a member of India's National Quantum Mission Expert Group. He serves as editor for multiple journals and is a senior member of IEEE and ACM. He also holds leadership roles as Vice President of the Data Science Society and the Vice Chairman of the Computer Society of India, Kolkata chapter. Sir, over to you.
Yeah, good evening, Professor Orpita, right, and good evening to all my colleagues who are here at this faculty development program organized by Techno India College and the ATAL FDP. So yeah, so we are already quite late in the evening, but still I hope that I will be keeping you engaged maybe for an hour, okay, from here. Okay, and what I will be speaking will be, I will be speaking on the very basic understanding of the quantum machine learning. Okay, and I hope that some of you through this FDP have already learned the basic postulates of this quantum computing. Okay, so I will give a very brief conceptual overview of that, and then we will discuss more about the the quantum machine learning, and that is how we can look into how we can use the quantum operations to do suitable machine learning techniques, to develop suitable machine learning techniques. Okay, so let me start my presentation. So I hope my screen is visible to all of you. If anyone can just say that.
Yes, sir. Yes, sir.
Yes, sir.
Okay, great. Okay, so the topic of my title of my lecture is Demystifying Quantum Machine Learning, which means that I will try to make the understanding of the machine learning in the quantum domain, which is thought as very complex, or maybe a little bit different than the classical machine learning in sense, to make the things very easy for all of you who will be attending this lecture. Okay, so this will be my agenda, very basics of quantum computing, and then I will directly get into this quantum machine learning, the various steps of the quantum machine learning circuit, and a bit on the functions what we use in quantum machine learning. Okay, some interesting use cases which I will just try to push very fast. Okay, and then the conclusion. Okay, so this is what is quantum computing. Okay, we know that that this is a journey of computing. Started with calculating machines, which were electromechanical relays, and then came the semiconductor, the silicon transistors, and the magnificent world of the VLSI technology, which squeezed the size of the hardware of the transistor circuits in our chips, right? And that enabled a huge computing power to a small chip, which is now having multi-core or many-core, right? Many functional processing units are there in a single chip, okay, right? And we have a high density of the memory, and that's why okay, we are having the fantastic devices like our smart devices, smartphones, right, which have very good computing capacity, being lightweight and being small, okay. But if you look into the journey of computing, the entire the entire journey of computing is that, hey, can I enhance my computing power? Okay, and that's why we moved from from 4-bit to 8-bit, 8-bit to 16-bit, 16 to 32-bit, and also we moved along single core processors to multi-core processors, and then the present domain of chiplets. Okay, so all this development in the computing technology, if you look, be hardware, be software, okay, it will look, the focus was that, can we increase the scale of computing without spending much computing resource? Okay, and so the next level of this particular thought process is an automatic advancement towards the computing, which involves the computing states of subatomic states of matter. Okay, which means that it can be electronic energy, it can be nuclear spins, it can be the polarization of the photons, okay, right, and many such subatomic states of matter, which demonstrates or which works in the phenomenon of quantum mechanical laws of physics, right? And why it is necessary? Because first of all, it is necessary because the squeezing of size of the transistor itself limits to the zone of single atomic layers, right? And once we hit the single atomic layer, what we have already hit, because we have the Intel technology of 1.5 nanometer transistors, which means that we are already hitting that particular domain or the particular dimension of the matter. Okay, for number one. Secondly, is that the famous lecture of Peter of Richard Feynman, in 1980, the Massachusetts Institute of Technology, where he said that if we want to simulate quantum physics, we cannot do it in classical computer. Okay, quantum physics should be simulated in a quantum computer, and we can actually find. And what is quantum physics, right? If we look into the present problems of maybe nutrition for the plants. Okay, I was listening to a lecture today, okay, where it was being spoken that if you want to look into the nitrogen, the nitrogen which is being nitrogen fixation, which is one of the major thing which is done for the development of the plants. It's a quantum phenomenon, right? If you look into the drug molecules, okay, it's a quantum phenomenon, right? The molecules of the drugs interacts with the receptors or the genes of the virus, right, and tries to inhibit those genes, and we have to study those. What is the perfect combination which makes the molecules? Okay, what the perfect combination of the drug atoms which makes the molecules and which inhibits the genes of that particular virus. Okay, so which means that these are all complex quantum phenomenon, right? Or the things which are happening in the space, right? And so these are the things which are actually quantum phenomena which are happening in the real world very deep. And if you want to understand those, okay, we need the quantum computers which can simulate or which can actually execute those functions in a computing system if it's quantum physics driven system, and that's quantum computing. The third and the most interesting part, okay, being the application development. In the side of application development, yeah, quantum computing also shows that it can do computing pretty fast, but pretty fast with less amount of resource. Okay, and that tells us that many of the algorithms which are pretty hard in classical computer can be better done, okay, with a less amount of time and less amount of energy in a quantum computer, right? And that obviously leads to the high performance computing capacity of the computers, and that also leads to the quantum computers. Okay, so let's look into that. What is this computing capacity? This is the key thought process, that why we should look into problems, right, and try to build quantum computers, right, and try to execute those problems at scale. That means in a quantum computer. Why? Because let's try to understand the basics of this. Okay, and in a very few minutes. The next few minutes I will just take, okay, to make you understand the basics of this. Okay, so we know in a classical computer, okay, the data is encoded in terms of the bits, okay, right? If I'm trying to store any integer or trying to store any character or try to store anything in my computer, right? I have to first encode it, right, in terms of a sequence of bits, and these bits get stored in the registers, right? And our computing process is nothing but trying to do a logical operation on the data stored on the registers, logical or arithmetical operations on the data stored on the registers, right? And try to generate a register value which is the result of my computer. But in every process, every step, what we are trying to do, we are working with the data represented by a string of bits, right? And each of the bits, right? Each of the bits in the string can only take a value of 0 and 1, which is a switch which is open or closed, okay? Now let's go to the quantum bits, which is called qubits. If you look into the quantum bits and qubits, the difference between the classical bits and quantum bits is that obviously the quantum bits can also have the states of 0s and 1, but those are the spatial states. Spatial states of a qubits are the states are when the qubit assumes a value of 0 and 1. Okay, but if you see my diagram here, right, you will try to see that I have also plotted, let me use the pointer, okay. Okay, yeah. So, okay, so if we look here, and if we look at, there are some other states also which are possible, because all these states are the solution of the Hamiltonian function of this quantum mechanical system, right? And these states can exist, right? And these states, what are other than the very definite 0s and 1, are called superposed states. Why this is superposed states? Because in each of these states, I get two values, okay? One is the probability of getting measured as 0, and 1 is the probability of getting measured as 1. Now, having said so, right, it is not that when I measure a qubit, I will get a true value, okay? When I measure a qubit, I will either measure it as a 0 or either measure it as a 1, okay? Then how the probability comes? The probability comes that if we just make blindfolded, right, and try to make 100 measurements on the qubit, on the same qubit, right? Depending on the probability, as we all know, probability that how many times it will result to 0 and how many times it will result to 1 is dependent on the probability of the 0 and 1. So generally a qubit is being defined in terms of 0, okay, that way one amplitude is associated with 0 and one amplitude is associated with 1, right? And the probability of the qubit getting measured at 0 is the modulus alpha square, right? And the probability of getting measured as 1 is modulus beta square. Why modulus? Because alpha and beta are complex coefficients, okay? So what does it mean? It means in a very simple sense that if I'm storing a generic qubit, right, it has two probability values I can store or I can associate in a single qubit. Now, if I increase the number of qubits, if I go from single qubit to 2 qubit, okay, we generate 4 probability values. If I go to 3 qubits, I generate 8 probability values. And if I have n qubits, I generate 2 to the power n probability values. And each of the probability values can be utilized to encode your data. Okay, so whatever data you have, suppose you have a capital N number of entries in a list. Okay, now we want to transfer it to a qubit system, qubit space. Okay, so how many qubits you require? You will require log of capital N qubits. Okay, because log of capital N qubits will actually, if it is small n, then 2 to the power small n equals to capital N. Okay, because now what happens is that in your n qubit system, you can store 2 to the power small n or capital N number of probabilities. Whereas in the case of classical, if you want to store n bits of information, okay, that means n information in a minimum possible way. If they are binary also information, you require n bits. A capital N information, single bit capital N information, you require capital N number of bits. Whereas in the case of Okay, a quantum system, okay, that will capital N number of information requires log capital N number of qubits. So which means that I have, if I just compare the computing capacity, I have actually created an exponential capacity, because smaller number of qubits can generate 2 to the power n number of spaces, okay, number of states, okay, where I can encode my data. And that's the computing capacity where classical computing goes very fast higher once we have an increasing number of qubits. But maybe it is not so visible if we have less number of qubits in hand, but if we have a sufficient number of qubits, the amount of data, okay, it can encode is so large compared to its classical counterpart, that gives us a tremendous advantage. Okay, now having said so, okay, having said the fantastic capability of the computing capacity of our quantum computers, there is a caveat here. There is a caveat here. Okay, so the caveat here is that once we try to increase this quantum qubits, okay, there is another thing which comes up, right? Okay, right. What it comes up is in terms of the errors. Okay, so more we try to increase the qubits, okay, the number of qubits, the amount of error a quantum system generates, right, is almost exponential to the number of qubits. So if we have 3 qubits, the amount of error, and compared to if we have 4 qubits, the amount of error will be almost of the 10 to the power, okay, then almost exponential to the number of qubits. So which means that though we are trying to increase the qubits and trying to increase the computing capacity, okay, but there is something error, okay, which is very predominant in this domain. Why? Because we are working with the subatomic states of matter, and we know the subatomic states of matter, okay, that means as we go down to the states of matter, okay, the amount of energy required to oscillate those states, to perturb those states, is also very, very low. So a slightest change in energy in the system will actually generate a sort of perturbation in those states. And also at that level of matter, the states are highly interactive. So in one way, we require a little bit of good number of qubits to actually have a very good computation, which is not possible in the classical computer. But on the other hand, if we try to enhance the number of qubits, there is a possibility that we are getting into larger errors. Okay, so that is the work what engineers and scientists are presently doing. So you don't see that, okay, that means this version of quantum computer comes with 200 qubits, right? And the next version of quantum computer comes with 1,000 qubits, and this is done within 6 months or 8 months or a year. It's not like that, because once we go higher in the scale in the quantum in the qubit space, the amount of error we have to control, that requires different levels of technology. Though having said so, if I see the journey of the quantum computers, around 2014, IBM started with their 5-qubit quantum computer. And if you look at 10 years progress, 2025, IBM with a distributed quantum computing has gone to 1,000 qubit quantum computer. And the promise is that within the next 2028, it will probably reach the 5,000 qubits quantum computer, which is obviously going to be a real platform where we can actually beat all the classical computers. Okay, so that's why we see that so much of things are going on or focused on quantum computers. Okay, the last but not the least, what we have to remember here is that, okay, though quantum computer is a fascinating thing, but quantum computer does the things in a very different way than classical, and quantum computers have a huge capacity and capability. But there is one thing: it's not that every algorithm will have a very, that means exponential speed up, or we can exploit the quantum capacity to best. So there are algorithms which we have to find out and which we have to map to the quantum system, right? And we will find that there is a gain, but there are also algorithms which doesn't have a gain in quantum computing. Okay, like every computing is not machine learning, right? There are certain class of problems which we can map to machine learning. Similarly, the quantum computing is also the same story, right? There are certain class of algorithms or computation problem which actually uses this high scale capacity of quantum computers very well, but there are algorithms which cannot exploit this, okay, due to the own reasons of the algorithm, and they can be well suited in the classical computing. Okay, so there are suitability of the processing. It depends that what type of algorithm you are actually planning to run on the quantum computers. Okay, just give me a minute, second. Just give me a second. Just something. Okay, sorry. Let me again. Okay. Yeah. Okay. So I hope this is visible to all of you, right? Okay. So so I will just quickly touch up that what is this system. I don't know whether you've already seen this particular system. Okay, this system defines a block sphere. Okay. Okay, it is visible. My screen is visible to all of you.
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So this is a block sphere which is called the state space of a single qubit system. This is very important, right? What is the state space of a system? If we just go to the vector space concept of the analysis, okay. So state space of a system is that it defines the space in which, that means every point in the space, right, defines a possible state where the system can exist. Okay, and we have the state parameters. What does it mean? It means that if we try to change the parameters, then I can move from state 1 to state 2 of the state space. So if we consider a qubit as a system, though it is really very difficult to imagine a qubit, okay, which is a subatomic state of a matter, is a system, but in terms of quantum physics or quantum mechanics, we will accept that this is a system. Okay, and this is the smallest possible quantum system in the world, a single qubit system. And what I show here is the state space of the single qubit system. What is the state space? The state space of a single qubit system is the surface. Okay, let me again take the pointer. Okay. Sorry. Let me get the pointer. Okay, so if you see the surface of this unit sphere, okay, then this surface of this unit sphere, and this particular sphere is the state space of the qubit system, and this is a unit radius sphere. Okay, this sphere has 3 axes, okay, x, y, and z, 3 axes, and the most common axis is the z axis. And obviously in the z axis or z axis, we have marked the two basis states. Why we say basis states, I will come to that. So the basis states across the z-axis is the north pole 0. And if you look into this sign is a little bit different than a normal 0 we represent classically. This is called a ket notation, which has a typical type of brace. If you see a straight and an angle, this type of braces are called the ket, which tells that these states are quantum states, not the classical states. Okay, so Z is one of the axes across which I can measure the quantum state vector, a single qubit quantum state vector, and the two extremes of the z-axis are 0 and 1. Okay, but what I show here is a vector which touches some point of the surface of this blosphere, and I name this as an arbitrary quantum state psi. Okay, why this is a quantum state? Because this is a point on the blosphere. From the center, I touch and go to the surface of the blosphere. Okay, right, and that is why it's called a state psi. Okay, it's called a generic quantum state psi. And what are the state parameters here? The state parameters here are the two angles. If you look into very carefully here in my diagram, you will find two angles. Okay, one angle is the angle with the state psi mixed with the z-axis, which is called the theta, and the other angle is the projection of the state psi on the xy plane. This is the projection of the vector on the xy plane. And this is the angle, and this projection makes with the x-axis is called the phi. And if we want to move the state from one point on the surface to the other point of the surface, right, what I need to do? I need to change the value of theta, which moves it across the z-axis. Okay, I may change the value of phi, which makes it across the xy plane, or I can change both. Okay, so ultimately, if I want to do a state change of this particular single qubit state vector psi, which is a vector from the origin of the sphere to the surface, which actually defines the surface on the blosphere, which defines a state, right? And if you want to change the theta and phi, I can come across different states in this particular state space, and the single qubit will occupy different states. Okay, and so that's why the rotation angles are so important in the quantum system, because rotations are the single qubit operations by which you can update the state of a single qubit quantum system or a single qubit quantum vector. What I show here with the examples is that if we try to change that, so this is a generic example of a state psi, which has a coefficient alpha corresponding to the 0 and 1 and sine theta by 2 to the power I phi, okay, corresponding to the 1, right? And if we make theta equals to 0, then this part, sine part, vanishes, and then the cos part becomes 0, which means that it perfectly becomes aligned to the 0 axis, so it becomes 0. If we make theta as pi, then this particular part, the cos part, vanishes, right, and the entire thing comes on this part, which is the one axis. So 0 and 1 are the two extreme values, okay, which we have, but in general it will have some arbitrary value of theta and phi, so which means that where the vector will be something in between 0 and 1, right? And then we define that cos square theta by 2 is the probability of getting measured as 0, and sine square theta by 2 and modulus e to the power I phi square multiplied will give the probability of getting measured as 1. Okay, that's why I said that a generalized quantum single qubit quantum state can store two values. Okay, now this is normal representation across the z-axis. There are other representations also of the qubit state. If we try to represent the qubit state across x-axis or the qubit state across y-axis, and those representations are interchangeable. Okay, as we see that a particular general psi, if we just put theta equal to pi by 2 and phi equals to 0, then we actually come to the positive x-axis. If we just do okay, theta equals to pi by 2 and phi equals to pi, we go to the negative x-axis. And similarly, if we change the values, the last two examples, if we change the value of theta pi by 2 and phi as pi by 2 and theta pi by 2 and phi as 3 pi by 2, we go to the positive y-axis and negative y-axis. So So this is also something which is pretty interesting in quantum. It means that the particular vector, what I am measuring, and the theta and phi, its projection depends on which axis I am measuring. So that is also an uncertainty in the terms of quantum state. It's not only that you have to know the theta and phi of the quantum vector, but also you have to know that across which axis I am getting the measurement of the phi, of the psi, and that is very well used in the quantum cryptography, or sorry, quantum communication in the key distribution. Though I will not touching that in this particular lecture, but that is also a pretty interesting phenomenon in quantum communication, that how we can actually communicate a state, right, encode a data in the quantum state, and we can okay, the if or the attacker will not able to get the data, okay, because though he can try to guess what is psi, but he doesn't know what is the axis over which the psi has been generated for a particular instance, okay, and that's why quantum communication is so secret, okay. Okay, I will just quickly, I think I have more 25 minutes to cover, okay, the next part, so I will just finish this part very quickly. And these operations on the single qubit are being defined, though I tell that, hey, I changed the theta, I changed the phi, but corresponding to all this theta and change phi, we have well-defined gates, okay, which are called Pauli gates, Hadamard gates, right, which are basically, if you are going in single qubit operations, okay, the gate operations can be modeled as a unitary matrix, right? And the dimensions of the matrix are 2 to the power n plus 2 to the power n, where n is the dimension of the qubit system. If we're going for a single qubit system, it is 2 to the power 1 plus 2 to the power 1, so it's 2 cross 2, right? And that's the way we can actually define the transforms which are operating on the single qubit states by actually defining the transforms as unitary matrix, and there are well-defined gate sets. Again, not getting into the details of that. You can get into any textbook for reference material, right? Okay, right, and you can understand. Okay, so these are the generic definition of this. Just I think if we just try to focus the most important part of this particular discussion. The most important part of this particular discussion is basically the last equation, right? Last equation seems to be very complex, but it means that if we try to describe the single qubit operation, so all these functions, okay, K delta, T alpha, R beta, T gamma, are the single qubit rotation operations. And this can be generalized as a matrix operation of as I said here. Now the question comes here that why it is so important and why I'm stressing here. This is required because, hey, I am trying to define the computation on a qubit system, right? And when we write a function, you don't think about the quantum system and try to define the function, right? You first of all define a function which will be something that, hey, I have a x and I get a y, okay, right? And then we try to find that, what is this function? The function, okay, the function is basically x divided by y, right? If x equals to u multiplied by y, okay, right? Now then x divided by y will give me the u. Now, provided I get an u, right, how I define the operation. I can get an u, but how I define it. So defining u means you have to decompose the u in terms of a sequence of single qubit operations, because those are only permissible if you are trying to look into the operation only on a single qubit. So this is a generalized form of a single qubit operation, sequence of operations which can be modeled as a matrix, and then you try to solve that. Then you try to define an equation. This may be a matrix solution, or a matrix solver you can use, and you can try to find what is my delta, what is my alpha, what is my gamma, right? And once we find this, solve it, you can tell that, hey, this operation was done by a sequence of single qubit operations. This is what is required, right? You need to synthesize your function in terms of quantum operations, and that's why it's so important. Okay. I will not get into this detail. So this is the as I said, that you can measure it across Z, I can measure it across X, and measure it across Y. Y, the same vector will have different values, right? And that's why it's a more important to know the vector and also the basis for measurement of the vector, right? To understand that what value the vector you are trying to generate or you are trying to get out of the vector, okay? In the summary, this is the sequence, this is the functions. Okay, so apart from, so if you see the right, the quantum computers, and on the left, the classical computer, quantum computers have the qubits, state 0s and 1, and there are also superposition states, okay, which have the probability of getting some probability of getting measured to 0 and some probability of getting measured to 1, right? In terms of the gates, it is a single qubit rotation gates. Also, there are gates which are, I will come to this coupling gates very soon here. There are also gates which actually work on 2 qubits, okay? Normally, 1 qubit is called the control and 1 qubit is called the target, okay? Right? And these are the only 2 primary operations that you can do in a qubit system: a single qubit rotation operations and the 2 qubit coupling operations. And these are all of the actual operations what you can do in the qubit, right? So whatever high-level algorithm you write, ultimately when you're trying to implement it into the quantum hardware, okay, right, you have to decompose them in terms of this, and there's a hell lot of things goes on for logic synthesis of the quantum, okay, right, and a lot of work has been done actually. That means, okay, if I go back to my PhD work, right, I will just CV that means I did all these things in my PhD, okay, right, and this is how we look into the quantum circuit, okay, where we try to define the qubits initially, right. There will be maybe some qubits can be defined as a 0, and some qubit can be defined as superposition states, which is generally represented by psi, right? And then these are all the quantum gate operations, right? And then I measure the qubit systems, qubit states, and I get a classical value of it. So we also require classical registers, okay, which will hold the value of measurements of the qubit states, right? Only one thing what we have to remember here compared to that means the logic circuits what we are normally interested in the classical computing is that this particular direction, okay, what we show across the x-axis from left to right is the time, not the space, okay? So what it means is that these are the qubits, okay, which are initialized according to your own way, okay, right? And then what it does, these particular operations, which are single qubit Hadamard, 2 qubit control knot operations, operates on these qubits over different intervals of time. So this is the first operation I do, okay, maybe in T1 time. This is the second operation I do in T2 time. This is the third operation I do in T4 time. And this is the fourth operation I do in T5 time, okay, because I'm taking initialization as T0, okay, right? And then I measure it and I get what I have done in this. So this is a quantum evolution. It's an evolution of the same memory, and that is also why quantum computing is called in-memory computing, right? And this in-memory computing ideally will save your lot of computing resource as well as energy, okay? Because we don't actually take energy to make the flow of your data from block 1 to block 2, from block 2 to block 3, what we normally do in a classical processor pipeline. Here there is no pipeline at all, okay? Here is only we have a bunch of qubits, and we have operations which are performed on the qubits in a time-spaced way. So there's no other extra hardware required, okay? Just the qubit system and the control signals which evolves the qubit system. And that's why the quantum hardware or the quantum architecture is a very different type of computing architecture than we normally experience in the classical domain, okay? So let's move on to the part of this lecture, quantum machine learning, okay? How interesting it is. So quantum machine learning involves, the quantum gates, okay, which tries to learn a feature space, okay? Using, so the basic crux of the matter is that, hey, what you try to do in a learning model, right? In a learning model, if you have a training set, a supervised learning model, what you try to do, you try to match, okay? You try to start from an input and you try to match the output given in the training data corresponding to the input, right? And And if you have used the training data well, diverse training data, and if your model during training, after some iterations of training, have generated the output close to most of the outputs with a very less amount of error, then you are sure that this particular model will work for the entire distribution. So similarly, what we try to do, so what are the, so there the tweaks. Basically, if it's a neural network model, our control over the weights. And now what we have here, so we have a so we first describe the input in terms of a qubit system. So that's the extra step we have to do. We have to try to take your classical data, and we need to encode it and represent it in the qubit system, qubit memory. Okay, first of all, now the measurements what you do. So if you see here, the measurements what you do will be the results. Okay, of your during your training, the results you get for the various inputs. Okay, so the measurements will give also the output in the quantum circuit coming from the same input. Okay, coming from the inputs which comes from the training, right? And in between there are circuits which are alpha, beta. These are the parameters, right? Why this is the parameters? Because these parameters are nothing but the gate parameters. So you operate certain gate operations on your input, and you try to map and you try to generate the measurement operations at the end from the qubit system, which maps your actual defined output in the training data, right? And if you can do sufficiently this, then you actually try to find out, solve the alpha, beta, the parameters of your gates, and you have done you have made your quantum circuit learn. But now a question can and now you can ask me that, sir, what is the purpose of doing it? Because we know that machine learning is already there, right? Why we are doing the same thing in the quantum, but what's the advantage? The advantage in quantum is that, try to look into this thing, right? So we do this training over multiple iterations, taking each sample at once and trying to find out what is the output for the sample, right? And we do this for an entire training set. Okay, now in quantum, right, you can represent the entire training data. Okay, suppose a list of capital N training samples. You can define the entire training data in terms of log capital N number of qubits, generate those in superposition, and you try to do that. But the other thing also you can do, you have a capital N feature values corresponding to each training data, right? And for each of them, you try to define a storage, and for each of them, the kernel computes. Okay, you have an WI multiplied by XI. So the XI is the input feature, right? And you do WI dot XI plus, which is W1 dot X1 plus W2 dot X2 plus W3 dot X3, and this you go on computing. Whereas in the quantum, you can define the feature space as superposition. So if you have a capital N number of feature values of a feature space, you can represent the feature space as log capital N, right? And then when you apply the function, it is applied simultaneously on the entire feature space, right? And so you apply the function on the entire distribution. That's the most important. So the training set is also a distribution, right? You apply the data on the entire, you apply the kernel on the entire distribution, and when you measure, you get the measurement for the entire distribution. So you are not getting into the sample space where in the classical you are actually sampling them independently and you are trying to look into their results independently, which doesn't make much sense because you cannot see the entire distribution at one shot. In the quantum, you can see the entire distribution at one shot, and you can know that, hey, if this is my input distribution, right, applying the quantum kernel operates on the entire distribution and it generates an output distribution, right? And that is so important to make your training faster. Okay, Okay, suppose I know that that means I operate. Suppose there's a physical problem, right? I'm trying to find that what will be the effect of a particular operation. Okay, say a particular. Suppose I'm giving that means suppose I'm giving food to the plants. Okay, each plant is an independent sample in my distribution. Okay. Now what I can do, I can actually one way is the classical, where we try to look into each of the interactions of the food and the plant. Okay, and we try to make a list and then we go. But we try to understand that what would have been if I have a technique by which I apply the food at one shot and I see this was my initial input distribution of the plants, and then I look into the output distribution just as an output of my operation. And that gives me so wonderful to understand that what has actually happened after I applied the kernel, right? And to minimize the loss and all this. So this is what is the quantum game, right? It is not a thumb rule that you can do this always, but you have to do like that, okay? Okay, so this is what is actually, so what is the crux of the problem here is that machine learning is understanding distribution. And I will tell you the clue here. Quantum systems are the best way to generate distributions at your will. I will show you that you can generate distributions at your will by using single qubit operations and 2-qubit control operations. Okay, so let us try to see. I will just keep a little bit of this. So this is the distribution I'm saying. What is the distribution I'm showing? I'm showing a distribution what a single qubit can generate. A single qubit in one very well-defined setting can generate a distribution where it has a 50% probability of getting measured as 0 and 50% of getting measured as 1. Okay, but if I just try to initiate the qubit not in entirely 0 or 1, but in a little bit bias, I can generate a distribution which is 60% probability of 0 and 40% probability of 1. And try to understand if instead of a single qubit, I now increase the qubit to 2, to 3, to 4, to small n, okay, then each of the distributions will be a joint distributions of all these qubits, and it will be really a distribution which is so wonderful, right? And you can create a distribution, okay, just like doing a single qubit, okay, like connecting single qubits and trying to make so different distribution, and it all depends that what operation you have done on the qubit and how the qubit was initialized. Okay, so that is one type of distribution. Okay, another distribution is that when we use the coupling gates. Okay, when we use the coupling gates, is called an entanglement. And what I show here in a very well-defined simple setting is that this is a well-defined distribution of 2 qubits where all the probabilities of all the states 0, 0, 0, 1, 1, 0, 1, 1 are pretty good. Okay, but now if I go entanglement, okay, which are I make the coupling stronger. If I make the coupling stronger, so if I try to make that, okay, there are only 2 qubits in the system, but there is no coupling between them, which called non-entangled. Because we can have two persons, but there is no interaction between them using the 2-qubit gates. They are 2 independent. Okay, then I can have a very well non-entangled distribution. But if I have a typical type of entangled gate operating between the 2 qubits, then I can just have disruptive distributions where I can just squeeze down some of the states. So I see that you squeeze down 0, 1, and 1, 0 states. Okay, and you can have in between also we can play, right? How strong is your coupling? How weak is your coupling? So you see that a 2-qubit system can generate so many distributions. And imagine what will be the distribution if we increase the number of qubits and do a tensor of distributions. So how many different variants of distributions you can create? And that is what is the crux of machine learning, because in the case of your training data, you need to match the distribution in your training set. And in quantum, you can match any distribution because you have the games to play using single qubit operations and 2-qubit control operations. Though having said that, how tough is the game, okay, depends on how many qubits you're handling, because as you are increasing more and more qubits, okay, right, the system becomes a very, very large number of sample space, and to operate on the large number of sample space, right, you require a good amount of resource, okay. So I'm just skipping it a bit. So now what we are trying to do here is that, okay, if you look into the previous quantum algorithms, when I started my research, there was no this parametric quantum operations. There were only very definite quantum operations, like algorithms coming from Shor, Grover, or these HHL algorithms. But now, if we look into the quantum optimization leading to quantum machine learning, you have parameterized gates, and these parameterized gates similarly works as the weights, or the weights of the neural network becomes the rotational angles of these gates, okay, right, and properly choosing the rotational angles, properly adjusting rotational angles, you can reach to the measurement space which maps your distribution, okay. And that's what's the entire game of the machine learning. And why you do better, again I iterate, because you can work on the entire distribution, okay, right, in a one shot, and you can visualize the measurement of the entire distribution at one shot, okay. So in order to, okay, so this is the thought process, but the first level is that, hey, I have a classical data, right? How I can map it to the qubit space? Because if you can map it to the qubit space, then only you can superpose that, and you can generate a qubit distribution equivalent to your data. Okay, so there are certain encoding techniques which are used in the quantum model. Okay, so the step one is EX, which is encoding of your classical data, and then there is a U theta, which is equivalent to the kernel operation, which actually takes the encoded space to a state where we can measure, and we can actually look into we can get that what distribution we have achieved, okay, at the output, okay. So the level one encoding is called the basis encoding. Basis encoding is a very simple, okay, but it is not scalable, okay. Like for example, if you have a features vector which having the feature values x1 to xk, right, you binary encode each of the feature values, right. And so it's an example, very toy example, right. Your x is a feature vector, and it has two features. One is having a value 1, and one is having a value 3. Okay, so you convert 1 to binary 0 1, and you convert 3 to binary 1 1, and then you use the qubits. Okay, so 0 1 is encoded in the first 2 qubits, and 1 1 is encoded in the next 2 qubits. Okay, but this encoding is not scalable, because try to imagine that if this number was large, then you require a large number of bits to represent this, right? And then if you have large number of values in the feature vector, right, this number of qubits would have been elongated. Okay, so you cannot because ultimately your target is that you have to use less qubits, because qubits are costly. So you cannot encode a very large dimensional feature space using this, having a large values. You cannot do that, okay. So the next operation is a very well handled operation called the amplitude encoding, where we try to encode this feature vector. Okay, we first normalize the values. So for example, again a toy example, suppose there are 4 feature values in the feature vector, 3, 1, 4, and 2. So we first normalize them. Normalize them means each of the values are being divided by the sum of the squares and then the square root of that. Because why? The reason is very simple. Because what we are trying to do, we are trying to map each of these values to the probabilities of the basis states, and all the probabilities squared sum to 1. So all the amplitudes what we generate will be squared sum to 1, and that's why we require normalization. So what I am doing here is that you try to understand here, there are 4 values, so I take 2 qubits, because 2 qubits can generate me 4 states, 0 0 0 1 1 0 1 1, and I store each of these feature values and the amplitudes of these basis states. So what I am doing, if I have a feature space of capital N having feature values, I normalize those feature values, and I put each of these feature values as an amplitude of the root to the power n base states, and for that we require log n number of qubits. Okay, and that is so good in the case of means if you have to encode a feature space having 1024 features, I require only 10 qubits. Right? If they have one values, okay. In the classical, to encode a feature space 1024, at least you require 1024 bits. Okay, that's the crux of the problem. So 1024 bits vis-a-vis 10 qubits. Okay, and the last part is that there is also a technique called the rotational encoding, where each of the feature values of the feature vectors are normalized and then pushed as an angular value of this of the rotation operation. So what do? We initialize the qubits with all 0, and then each of the features will modulate each of the qubits. So this is actually capital N. So for capital N feature size, we require capital N qubits. We don't get something like a logarithmic what I can say, logarithmic savings, sorry, exponential savings, what we did in the amplitude encoding, but here also it works well, right? Why I will come later, very soon. Okay, so there's this is called sort of angular encoding, where we try to put these values, normalized values, as the angles by which each of the qubits are rotated. Okay, right? That's also an encoding. Okay, and this can go like this. Okay, where we can actually try to do the rotations of the various axes, okay, for the various features. Okay, so we can rotate across Rx, rotate across x-axis Rx operation, rotate across y-axis Ry operation, rotate across z-axis Z operations, which means that we are encoding the same vector across 3 axes, 3 different ways, right? And each of these can be a particular feature value of the vector, right? And we can do further. We can do further on this, which is called I will just come to. It's called it's called a superposition, and we can do it over a tensor space, which actually means that if you are trying to do if you are try to do 2 to the power n samples, and each samples having maybe capital N feature space. So what we do, we require, first of all, we require log 2 to the power smaller number of qubits, and for the feature space we require capital N operations, and that is also a game what we play to actually generate the qubit feature maps. Okay, and these are all the things I'm now just trying to maybe we are trying to do. This is the entire circuit. Ultimately it looks like, okay, so once we have the data encoding, okay, right, these are the encoding part, okay, this is the kernel part, and this is the measurement part. Okay, right, and this is the way how we, and sometimes we use the classical computing also to optimize the parameters. Okay, right, so there is always said that we require a classical quantum hybrid thing. Okay, because quantum initial, okay, making the training of the quantum, okay, might require to optimizers, right? And those optimizers can be classical optimizers. But once we optimize this and find the suitable theta, okay, the trained quantum network works very fast. Okay, that means and a very low resource of, okay, compared to the same dimension of the classical problem. Okay. Okay, so this is the summary of what I have discussed today, which means that, okay, in the case of classical, we actually map the X to the kernel space, right? And in the kernel space, the measurement gives you whether it's the class probability of class 1 after the operation of kernel. It gives the measurement probability. Suppose we are doing softmax, the probability of class 1 or probability of class 0. In the case of quantum, first we encode, this is the quantum part, we encode the X to a Hilbert space, to a qubit space, right? And then in the qubit space, we actually try to try to define a sort of quantum transform which maps it to a measurement space, right? And the measurement space gives you a value high or low for the certain for the certain samples, right? And we can generate a sort of classifier out of that. Okay, so it's called the expectation value of a measurement. So we try to find that after an operation, whether this particular sample of the distribution has an expectation value for class 1 or class 2, right? And that can be very well done by the measurement operation, which can be done in the quantum domain. Okay, so these are some of the things. I will not get into details. So this synthesis of the circuits, there are called answers, and there are a lot of things you can get into that. How I can generate these U theta gates. It may be a sequential operations of R theta, or it can be an hybrid operations of R theta, and with coupling with some 2-qubit operations. Okay, these are different types of decomposition and synthesis techniques which we try to go for the variational quantum circuits or parameterized quantum circuits. Okay, and I think I will just skip to all the things. And there are a lot of use case you can do. Use case and drug design. Not getting into details of that, but there are ITEC separate the ITEC lectures and courses on quantum computing, right? In the various intervals. Now presently I'm taking a course at our radio physics department for the special paper on quantum computing for the VLSI students. Okay, right, and also probably I will be coming with a lecture series on IEEE pretty soon. On this, and these are the things you can also learn from other references, other lectures, where you look into that. Hey, quantum drug design. Find the spectral analysis, large dimensional data, spectral analysis, which is very much important in terms of image processing. Okay, when we are looking into certain problems of image processing, having a large number of multi-scale spectrum data. Okay, there are applications of actually allocating the channel in the 6G network, radio applications, communication applications, where we have to analyze the number of communication channel required for the number of nodes which are communicating in a particular using a particular backbone network. Okay, so all these problems have been optimization problems. Okay, right, and people have found or learning problems based on the data given. Okay, and people have found very good references. I show you that. Okay, that how you can get into this particular these applications. Okay, very well done. Okay, these are the good references you can find. I will not get into all these things. But this is a very beautiful thing which is being done by the QTAC in general, not in quantum machine learning, but in general quantum. QTAC is a consortium of various quantum applications and technology companies. Okay, right? It may be IBM, NVIDIA, Qualcomm, Fujisoft. Okay, whatever you name, right? Google. Okay, most of the companies are there, and and if you look into the roadmap of QTAC or the white paper of QTAC, you will find that there are verticals of engineering problems, right? And there are the things what you can do using the quantum computing in the various solving the various problems occurring the various domains in engineering and business. Okay. Right, I will just skip this, and this is what is a one particular work, and there are a good number of work going on with the industry with our group, but this is one of the things what we do with HCL Tech at Noida. Okay, right, we have an Indian patent, we have an US patent with them. We do a bit of quantum random number generation. We look into quantum optimization problems. As you know that our group owned the first quantum resource access award in India 2021, right? Mrityunjoy, my PhD student, is now the lead principal quantum engineer at ATAL Technology. Okay, right, we look at a lot of problems in quantum algorithms jointly with ATAL Technologies. Okay, these are the fantastic students. That means all the students have have got into good positions in industry. Some of the students like Nivedita, who is in PwC and works with me in quantum, and some of the good postdocs and interns, working with me, and we are more Two students joined me this year, last year, right? And I haven't included their name here, but they're also started working. Now we are a very big group. Okay, we are looking into a lot of problems from the industry. Okay, like either IBM, NVIDIA are already supporting us with the infrastructures. Okay, with the computing. Okay, we are working with LTI Mindtree. We are working with SIDAC. Okay, and some of the startups. Okay, we are working, right? And our group looks into obviously the quantum circuit and quantum synthesis, which was our bread and butter at least before the quantum algorithm machine learning came. But then the flurry of quantum algorithms, machine learning, our group developed, I think, a good number of algorithms in the quantum domain from that means, and which were multi-valued logic, which were on graph search problems, binary valid tree, quantum ant, right? All are contributions from our group in India, right? And now we're looking into quantum machine learning in a collaborative way with multiple groups, okay? And quantum cryptography we have recently started with our students, right? And we have collaborations. We look forward to more good and more intense research in this domain. And I'm very open to all of you, right? If you want to participate in quantum algorithms and quantum machine learning, or maybe we are today morning today afternoon we have a session with Keysight, where it's a different things we were discussing. Yes, our lab in India is also the first lab in India which have jointly with Keysight Technologies we have developed and simulated the qubit system, the physical qubits. The simulated qubit systems. Okay, right, and that's a contribution of one of my students from VLSI course. He's doing the master's project thesis with me, and we have already developed the 5-qubit simulation, and we are trying to develop more simulations. And once we are fine with the qubit simulations, we can integrate the quantum algorithms, and we can generate a compiler which will take the compiler, we will take it from the algorithms domain, maybe machine learning or maybe optimization, and we will trying to generate the exact quantum sequence, which will hit the qubits, right? And we will try to generate the less error operations on the qubits in bridging this particular gap, from quantum algorithm and circuits to the physical quantum systems. Okay. And that's all. A lot of things needs to be done. We are just touching a bit of this quantum. Okay, a lot more quantum will be coming, a lot, and across the world. If we see, the research is going great. That we might be sometimes we feel that we are doing slow. Across the world, if you see, it is really big groups, good groups, strong groups are working in quantum domain. And we should be. That means I think one of the purpose of the FDP was to motivate all of you to think about the contribution in the quantum computing domain. Okay, that's all. We have about fantastic references in terms of quantum machine learning and quantum optimizations. I will pass this this PPT to all the organizers so that all of you can get these references and can look into those and can try to find the fundamental problems in the quantum optimization and quantum machine learning. Okay, yeah. So thank you all. I'm not keeping you very waited for the dinner time. Okay, and thanks for connecting, giving the opportunity to connect to all of you. Okay, today. Okay. Yeah. So thank you all. I'm done. Huh? Yeah, I will be providing the PPT. No worries. Yeah, I will be providing the PPT to to Ma'am Professor Orpita. Okay, right, and you can all use it for study, but there's a request that don't use it. Okay, for the presentation. You can use it for the classes. I'm fine. Okay, but don't use it in a professional presentation because there are some copyright issues on this particular presentation. Yeah.
Thank you, sir. Thank you, sir, for this very important and insightful discussions. Can you take one or two questions from the participants?
Yeah, sure. Please. Yeah, please go ahead. Please. Yeah.
Participant, if you have any queries. Any queries from the participant?
আচ্ছা পরে বলছি ওটা তুই চাপ নিতে হবে না থাকলেই পেয়ে যাবে তুই রাখে বলছি না
Hello.
Late in the
Yeah,
evening.
good
So,
evening, sir.
okay, good evening. Yeah, please go ahead. Yeah.
Yeah, I'm Narayan from SG Balakunda Institute of Technology, Belgaum, Karnataka.
Okay.
So I'm working on VLSI. I thought to implement this quantum machine algorithm in VLSI based design. So how will it be helpful to implement these machine learning algorithms for VLSI domain? And at what level I can?
Yeah. First of all, machine learning. Obviously, we have to look into that. But I think that as you are doing VLSI, right? I am also a. I started my career as a ED engineer. So what you can try to look into the graphs, okay? Because you know that the circuits are nothing but the circuits are structured in forms of graphs, okay? There are beautiful algorithms on quantum graphs, okay, which can do the certain graph-based optimizations or maybe graph search operations, or there are QAOA where we try to define the weights in terms of the exponential phase parameters, right? And you can actually make those the high weights working fastly, that means decreasing to the that means decreasing their contribution very fast in the optimization function, okay, because it goes to the phase part, exponential phase part, right? And the effect decreases very fast, okay? So that helps in the optimization to reach the optimization faster in a quantum system, okay, that means in a quantum setting of graphs of the data class. In terms of optimization, people are trying in terms of graph-based machine learning, people are trying something called QGNN, where a quantum graph neural network. You can also look into the problems which are coming up very soon, which is called topological, okay, quantum algorithms for topological graph, okay, right? And that is also very important, very important things which are going on. You can get into some of the new works which have been done on topological graphs and try to quantum algorithms for topological graphs, okay, quantum encoding for topological graphs, and try to find the applications for them in VLSI circuits. Yeah.
Yeah, thank you, sir. So it means we can do it at a simulation level. So how about at device level? Can we do this optimization?
No. Machine learning is only to see, you use machine learning to actually try to predict something, right? Or try to classify your fault, what has happened. So machine learning is either used for diagnosis,
Yeah, sir.
detection and diagnosis, or machine learning is prediction, right? So what you do in a VLSI design is that where you use machine learning, as I have some knowledge on that particular domain, it means that sometimes you cannot actually map a placement, okay? You cannot actually map a placement directly, okay,
Yeah,
right? And
correct, sir. Yeah.
because it can generate a lot of noise, okay, a lot of signal integrity issues are there, a lot of power
Sir.
all issues are there.
Yeah,
So the
integrity
thing is
issues.
that,
Yeah,
and
sir.
also when you try to update your VLSI design, right, you need to know that what are the corners it are generating. So this is the prediction problem in VLSI design, where you try to, before you actually generate the layout, you try to find from the circuit design itself that what are the issues which can generate in the layout, so that because generating the layout and then coming back is a costly affair. Okay, so basically machine learning is used for predicting what will happen in the next layer, so that it is not that you complete the layer, you verify, and then you see that, oh, something has happened, so come back in the previous layer. And these iterations are very costly in the VLSI design. So what is done is that, can we predict the things which will happen in the next layer from the layer what I have designed here, right? Or maybe the next 2 layers what I have designed
Fine,
here,
sir.
if you are focusing on the design only. Okay, in terms of VLSI technology, in terms of defects, in terms of yields, there are other parameters of predictions which you do. Okay, so what you need to do, you need to actually try to find out that, okay, what is the machine learning problem you are trying to do, right? You try to encode your data in the qubit state space, right, and try to find the proper kernel function which will map to your training data outcome, and try to see, once it is being trained, okay, you know that you can encode a very large data using small qubit, right? And the entire function can work on the entire distribution of the feature space at one shot, which makes the okay, which makes the learning as well as the execution faster. Okay, so we can, so we can discuss this maybe offline, right? I can help you to formulate the problem, okay, on the
Yeah,
domain.
sir, definitely. I will get an email ID from team.
Please.
Yeah, I will just mail my problems.
Excellent. Sure,
Yeah,
I will
thank you.
try to help. No worries. I will try to
Sir,
help.
fine. Yes, sir. Thank you so much, sir. It was very insightful session.
Thank you.
Thank you, sir.
Any other queries? Okay, so let us stop today's session. Thank you, sir, once again for this wonderful session. Thank you, participant. Tomorrow, we will again meet at 6 p.m. Day 2, Session 3. Thank you.
Thank you all.
Good night.
Yeah, thank you all. Good night.
Good night.
And I
Yes,
hope we
sir.
will
Good
meet
night.
again.
Yeah, good night.
Thank you.
Good night.
Take care. Bye. Bye.
Bye, sir. Bye.